We will now investigate how to find a best fit line between data sets X and Y. So suppose that we are given data on the relationship between two quantities X and Y. So what we have are pairs of data points, X1 and Y1, X2 and Y2, all the way down to Xn and Yn. And suppose that X and Y have an approximately linear relationship, meaning that Y is equal to B0 plus B1 X. Now, normally you are used to your linear relationships looking like Y equals mx plus b, right? But this time we're going to write it as maybe Y equals b plus mx, okay? But in statistics, they like to use b0 and b1 for the intercept and the slope. And the reason why is if they want to add a quadratic relationship, then they can say there's b2 x squared. And if they want it to be cubic, they can say it's b3 x cubed. And so there's some sort of standardization to those coefficients. Okay, so the intercept we will refer to as b0. And then the slope we're going to refer to as b1. Our goal is going to be to find the slope b1 and the y-intercept b0 that best fits the data. Now, in order to achieve that goal, we first have to ask the question, how do we define what is the best fit? And the answer is we're going to be looking for a line that minimizes the sum of the squares of the error. Okay, so what do I mean by error? Well, the error from estimating a data point y sub I by the corresponding point on the best fit line. Now the corresponding point on the best fit line I'm going to call y sub I hat, because y sub I hat is going to estimate y sub I. But what is it given by? Well, what we're going to do is we're going to plug in x sub I to our best fit line. And so if we plug in x sub I to our best fit line, then that will give us the point on the best fit line that is going to be closest, okay, to y sub I. And we'll call that y sub I hat. And so the error is going to be the data point y sub I minus the estimation of the data point y sub I hat. This is a vertical distance between the points y sub I and y sub I hat, and we call that a residual. I think a picture will help explain what's going on here. So I want to show you a diagram. And our diagram shows the residuals for the data points x and y. So we have data points x1 and y1, x2 and y2, x3 and y3, etc. And then what we have is points on the line that are closest to x1, y1, x2, y2, etc. Okay, so this point right here that's on the line will have the same x value. Here, x1 is that x value. So it'll be x1 and then y1 hat, because we're trying to estimate x1, y1 with the point that's closest on the line. Okay, so let me show you another one. This point here would be xn. The point closest is going to be xn, yn hat. How do we get that? We're going to plug in xn to our best fit line. Okay? And this point is going to be the closest point on the line to our actual data point xn, yn. Now the residuals are going to be these red distances between the points and the closest points on the line. Okay, so here E1 is the distance between our data point and the closest point on the line. This one would be E2, this one would be E3, and this one would be En. These are our residuals. Okay, that's giving us a sense, these values are going to give us a sense of how close our points on the line are to the data points. So now our goal is going to be to minimize the sum of the squares of the residuals. So I actually have written SS residual. That's the sum of the squares of the residuals, which is going to be the sum from I equals 1 to n of y sub I minus y sub I hat squared. So for each data point, we're going to take the actual data point y sub I and subtract our estimate of y sub I, and then we're going to square it. So you might say to yourself, why are we going to minimize the sum of the squares of the residuals? Well, these distances that you can see, E1, E2, E3, some of them are positive, some of them are negative. So the squares are positive. And if, of course, we square those errors, this will penalize large residuals. And it'll reward small residuals. So if we want to minimize the sum of the squares of the residuals, right, what we're trying to do is keep us from having large distances between the lines and the points, the data points, and we want to have instead small distances between the points and the data points and then the closest points on the lines. Okay, so what we're essentially doing though is we're minimizing essentially variance. This kind of calculation we've seen before where we look at the square of the distances. That's what we were using when we made that variance calculation. And so if this sum was divided by n minus 1, that would essentially be the variance, right? Well, if that's the variance, then what I'm saying is that this line, okay, this line that you see here actually represents the mean. Okay, so we're taking each data point, we're subtracting the mean, and we're squaring it. That sounds like a variance calculation. Okay, so this line that you see here, right, that represents the mean. And our goal is to minimize variance from the line. And of course, the line represents, in this case, the mean. Okay. Now, how do we actually minimize this quantity? Okay, so we have this sum, and I want to know, like, how do I minimize that quantity? Okay, well, I think what's hidden in here that you can't see is that y sub I hat is a function of two variables. Okay, it is b0 minus b1 or plus b1x. And so what we have is it's a function of two variables because it's a function of the intercept and the slope. And those are the two things that we do not know. We do not know intercept and we do not know slope. And what we're hoping to do is minimize this, okay? Minimize that quantity by varying the slope and the intercept of our line. So how do we minimize quantities? Well, that's an optimization problem, right? And you should be a little bit familiar with optimization problems because you've probably taken calculus, okay? And so what we have to do is turn this into a calculus problem where we're essentially finding a derivative and then we're trying to set that equal to 0 and then look for minimums. What makes this hard is that this is a multivariable calculus problem. And that's because y hat is a function of b0 and b1. But if y hat is a function of b0 and b1, then my sum of squares residual is a function of two variables, those two variables being the intercept and the slope. Okay, so this ends up being a multivariable calculus problem. The good news is that this has been solved, and it's been solved once for a generic set of data, list of x's and y's, and then we can apply the result of this to any data set. Okay, so this has been solved in generality already. So our definition here is the least squares line, or the regression line, is the line that minimizes the residual sum of squares. This is going to be our best fit line, okay? And the equation of the best fit line is given by y hat equals our intercept b0 plus our slope b1 times x. And then it turns out that b0 and b1 have some really nice simple formulas. b1 turns out to be r, our correlation coefficient, okay, times the standard deviation of the y's divided by the standard deviation of the x's. So this is a standard deviation of y's, and this is the standard deviation of x's. And then how do we find our intercept? Well, imagine that I plug in the mean to our best fit line. So y bar equals b0 plus b1 x bar. It turns out that that relationship has to be true. If I plug in the mean for x, I need to be able to get the mean for y. Okay, that's because the line actually represents the mean. So if I solve for b0, b0 is just going to be y bar minus b1 x bar. And so you can first find the slope and then essentially find the intercept in the same way that you've always done, which is if you know one point on the line, then you can find the intercept using the slope. Okay, let's do one example. Okay, so our example is going to be our global temperature change data. And so the scatter plot shows the change in global temperature Y versus CO2 concentration in the atmosphere. And we want to find the best fit line. And what I've done is I've given you a summary of all of the data right here. So all the summary statistics that we might need to know. What I want to do is figure out what is the best fit line. So I'm going to start with the slope. The slope is going to be r times, and this is going to be, let me just double check the formula. It's going to be the standard deviation of the y's divided by the standard deviation of the x's. Okay. And that's going to equal, in this case, r we determined earlier was 0.693. Okay. Now, you can use your favorite statistical software to essentially find the standard deviations of x and y. For y, it's going to be 0.342. For x, it's going to be 31.551. And that gives us a slope of 0.0104. Okay, so that is our slope, and our intercept in this case is going to be y bar minus b1 x bar. So y bar is 0.367, that's the average global temperature change, minus the slope, 0.0104. You might be curious about what the units are. The units here are going to be degrees Celsius divided by parts per million. And we're going to multiply that by something in parts per million. That's 358.593. That's the average of our CO2 data. And it's going to give us a negative 3.371. Okay, so our regression line is y hat equals negative 3.371 plus 0.0104 x. So what's the interpretation of the slope and the intercept? Well, the slope says for every 1 part per million increase of CO2 in the atmosphere, the global temperature increases 0.01 degrees Celsius on average. And that's important, okay? That doesn't mean that if you increase the CO2, you're absolutely going to get a 0.01 degree increase, okay? It's how much it's going to increase on average for every 1 part per million increase in CO2. Now that sounds okay. Okay, 0.01 degrees increase for every part per million doesn't sound all that great. Okay, but if you look at this graph, you can see that since 1960, which is where this starts, that CO2 in parts per million has increased from closer to 310 million to 410 million parts per million. So it's increased 100 million. 100 parts per million, sorry. And so what we could say then is that 100 part per million increase, right, tells us we're going to get a 1 degree Celsius increase. See, if we multiply everything by 100, okay, and that 1 degree global temperature increase is a dramatic increase that's having all sorts of effects on our global climate. Okay, what about the intercept? Okay, so for the intercept, right, that's where x is equal to 0. Okay, so that means that if there were no CO2 concentration, right? That's what x equals 0 means. There's no CO2 concentration, right? Global temperature would be minus 3.37 degrees Celsius from the 1960 reference point. That's the interpretation. Unfortunately, if you look at our plot, okay, you will see that if we were to go back down to 0, that would be far outside of our data range that we're looking at. And so we can't necessarily extrapolate all the way down to 0. So I'm not sure that if we had no CO2 in the atmosphere that we would have a global temperature that was 3 degrees lower. That's probably not realistic. You shouldn't be extrapolating beyond where your data lie here, or at least far beyond where the data lie. But nevertheless, that is a way we could interpret the intercept if we choose. And again, it makes a little bit more sense when the intercept is closer to your data range.